Bandwidth modulation. The next example illustrates the effect of negative feedback on the bandwidth. Suppose the feed-forward amplifier has a one-pole transfer function A of S equal to A naught by 1 plus S by omega naught, where A naught denotes the low frequency gain and omega naught is the 3 dB bandwidth. What is the transfer function of the closed loop system? From equation we have y by x of x equal to A naught by 1 plus S naught omega naught by 1 plus beta A naught by 1 plus S by omega naught is equals to A naught by 1 plus beta A naught by plus S by omega naught A naught by 1 plus beta A naught by 1 plus S by 1 plus beta A naught omega naught. The numerator of equation is simply the closed loop gain at low frequencies as predicted by equation, and the denominator is the pole at 1 plus beta A naught omega naught. Thus the 3 dB bandwidth has increased by factor 1 plus beta A naught, albeit at the cost of a proportional reduction in the gain. Figure bandwidth modulation as a result of feedback. This the increase in the bandwidth function fundamentally originates from the gain desensitization property of feedback. Recall from equation that if A is large enough, the closed loop gain remains approximately equal to 1 by beta even if A experiences substantial variations. In the examples of figure, A varies with frequency rather than process of temperature, but negative feedback still suppresses the effect of these variations. Of course, at high frequencies A drops to such low levels that beta A becomes comparable with unity, and the closed loop gain falls below 1 by beta. Equation suggests the gain bandwidth product of a one-pole system does not change with feedback, making the reader wonder how feedback improves the speed if a high gain is required. Suppose we need to amplify a 20 megahertz square wave by a factor of 100 and maximum bandwidth, but we have only a single pole amplifier with a open loop gain of 103 dB bandwidth and 3 dB bandwidth of 10 megahertz. If the input is applied to the open loop amplifier, the response appears as shown in figure A, exhibiting long rise time and fall time because the time constant is equal to 1 by 2 pi f 3 dB, similar to 16 nanoseconds. Figure amplification of 20 megahertz square wave by a 20 megahertz amplifier and B cascade of 200 megahertz feedback amplifiers. Now suppose we apply feedback to the amplifier such that the gain and bandwidth are modified to 10 and 100 megahertz respectively, placing two of these amplifiers in a cascade. Figure B, we obtain a much faster response with an overall gain of 100. Of course, a cascade Of course, the cascade consumes twice as much power, but it would be quite difficult to achieve this performance by the original amplifier even if its power dissipation were doubled. Non-linear reduction. A very important property of negative feedback is the suppression of nonlinearity in analog circuits. We defer the study of this effect to chapter. Thank you.